Okay, so from the last lecture, we started to discuss some kind of the new generative model, which is the flow model. And after we started to discuss the flow matching, the thing is that it's quite confusing in terms of that now we are also changing many things in our basically the terminology and also the notations. But the thing is that basically in the diffusion model, the context, we defined the time range from the going from the capital T to the all the way to the zero in the generative process. So that's why we call this kind of the generation the process in the diffusion model as kind of the reverse process, right? But in the flow matching the context, we are now changing the time domain in terms of that the time goes from the 0 to 1 in the generative process. So when you say like the x0, that was basically the sample from the reference, the base distribution, and the x1 was basically the sample from the data distribution, right? So we are having this kind of the time, the changes. And also in the context of the flow matching, we are discussing basically three key things. Like one is the flow map, and also the vector field, and the probability path, right? And we also discussed how these are basically related to each other. Basically, the vector field could be computed as kind of the derivative of the flow map. And also the relationship between the vector field and the probability path could be defined based on the Fokker-Planck equation, which was basically defined in this way. So from this, what we could see is that we could consider basically encoding the information of the flow map by training a neural network, which is basically implicitly representing the flow map basically by modeling the vector field. Then we could basically see such kind of the neural network, which is kind of similar with the noise prediction network in the diffusion model case, right? So in terms of that, now we are having the network that can predict the velocity for the arbitrary the xt, the intermediate data point, and also the time t there as well. The thing is that obviously we don't have any kind of the closed form expression for the target the vector field here. So that's why we started to discuss the conditional flow matching. So in this context, we also discussed the three things: the conditional flow map, and the conditional vector field, and also the conditional probability path, right? And we also have seen some kind of some special case where the conditional flow map is defined as some kind of the linear function with respect to the x0 here. So given that the conditional flow map is defined as kind of the linear function like this, and when we also assume that this x0 is basically a sample from the standard Gaussian distribution, then we could also see that the conditional probability path is also defined as kind of the Gaussian distribution like this. And by taking the derivative of the flow map, we could also compute the vector field like this, right? So this was because like one specific way of like defining the conditional flow map. And we also can further specify those kind of the two parametric functions, right? The sigma function and the mu function here. So like one special case that we have seen last time is that basically simplifying everything in terms of that we are even making the flow map as kind of the interpolation between the linear interpolation between the x0 and the x1. Then everything becomes like simple like this in a way that we have the Gaussian, the probability path, and the linear the flow map, and also the vector field. So we can say that here the velocity is really defined as kind of the direction along the straight line between the x0 and the x1, right? And the other option is basically that we are following the trajectory of the diffusion models, the VP, the case, in terms of the define the probability path as like this, then the vector field was also defined like this from the relationship between these two. So given this kind of the two ways, or basically this is kind of like more general form to define the flow map. And based on that, we could basically train the neural network predicting the velocity like this. So this was like quite similar with the training of the diffusion models. And this is actually the case like when you have some kind of the closed form for the conditional probability path. So for the more general case, even when the analytic form of the conditional probability path is not available, we can still consider training the flow map like this. So here, basically, what you can see is that the small difference is that instead of like not only just like sampling the x1 here, we are sampling both the x1 and the x0, the pairs of like these two. And based on that, we compute the intermediate data point xt using the conditional the flow map and also compute the velocity. And also based on that, we could consider basically train the velocity prediction, the neural network using the L2 loss like this. So this also becomes some kind of the more general form of training the flow map. Any questions on this? So as we have seen last time, what we are going to discuss for today briefly is about more like how this kind of the flow map is basically related to the diffusion models. So actually what we are going to see for today is that actually we can consider the flow model is kind of the same with the diffusion model. More precisely, actually the flow model is kind of the generalization of the diffusion models. So in the way around, basically diffusion model can be seen as kind of some special case of the flow models. So diffusion model was the case that we are basically learning this core function, right? And the flow map is now the case that we are learning the velocity, basically the vector field. So it's basically a matter of like, which one we see as kind of some major factor defining the models. In the diffusion model case, we basically first demodeled the probability path, and based on that, we define the other things, basically the trajectory and also the velocity as well. In the flow model case, we first define some kind of the first model, the conditional the flow map, and based on that, we can also derive some kind of the conditional the vector field and also the probability path as well. So this is basically different kind of the perspective to define some kind of generative models, but actually we can see that these two are basically having some kind of the close relationship each other, which means that like one can be computed from the other. So which means that even when you have some kind of the pre-trained diffusion model, from the pre-trained model, we can actually compute the velocity and treat the pre-trained diffusion model as kind of the flow model and perform the generation the process as well. So this is kind of the interesting aspects. So if we also see the variational diffusion models from the perspective of the flow matching, but actually then we can say that it's kind of the special case that we are having a linear, the Gaussian, the conditional flow map, which is defined like this. So here the thing is that now, so sorry for the confusion with the many the new notations, but the sigma and the alpha function, those sigma and the alpha function, these two functions are basically the same functions that we have seen in the definition of the variational diffusion models before the first test, okay? Don't get confused. So these are basically the functions that we have used when we define the variational diffusion models. So in the previous lecture, actually, the positions of like these two functions kind of switch it like this, alpha and the sigma here. But now we have the sigma and the alpha. And the reason for that is that now we are also changing the time domain, right? So here basically it can be confused, but x0 here is the sample from the reference distribution, and the x1 is basically sample from the data distribution. Okay. So after basically changing the time range, now we are having the sigma and the alpha functions here, right? The same definition of the variational diffusion models. So we are going to basically see the variational diffusion models from the perspective of the flow dematching. And before we get to that, let's briefly recall some kind of the old topics. Do you remember this, the Tweedie formula? This is basically exactly the same slide I've shown in the lecture 5, I guess. So when you have some kind of the unknown, the prior distribution, and the Gaussian, the likelihood distribution like this, and when the marginal distribution is basically defined like this, the Tweedie formula is about basically computing the expected value of the mu here, which is the sample from the prior distribution, given a sample from the marginal distribution. So basically here, this is the case that we have some kind of a sample of the x, which is actually defined as like, which distribution is defined like this, as kind of the combination of the Gaussian, the likelihood, and also the unknown, the prior distribution. So given the sample the x, what would be kind of the expected value of the mu, which was basically the sample from the prior distribution. And what we have seen from the Tweedie's formula was that this is exactly the same slide that we have seen in the lecture 5. So actually the expected value of the mu given the x could be computed based on this core function, right? Using this core function like this. So this was basically the first time we started to see this core function. So if we have some kind of the quick quiz here. So now we are basically having this kind of the linear function, linear interpolate of the x0 and the x1, given these two functions, which is now computing x here, right? So given the x there, what would be kind of the expected value of the x1? Here, basically, the thing is that x0 is basically a sample from the standard Gaussian distribution, right? This is basically the known fact. From the fact that the x0 is basically the sample from the standard Gaussian distribution, given the x from the intermediate data point, what do we basically expect the value for the x1? Can you quickly compute this? So did everyone get this? This is kind of the same as like what we have seen in the previous lecture, right? We only basically use the only difference is that we are now using this like alpha and the sigma, the functions that are used to define the variational diffusion models. So I'm going to basically update the lecture slide, including all the answer after the lecture. So you can just like download again. So yeah, so thing is that this is basically exactly the same thing. From the diffusion model, we could see that we can compute before we perform like all the generation the process. We could basically compute the expected value of the final output from the intermediate value, right? Exactly the same thing. We are just like introducing the alpha and the sigma functions, defining the variational diffusion models, and changing the time domain that it goes from the 0 to 1 in the generation the process. Then we get this, right? So this is the part that we basically introduce this core function here. And also we have seen basically the relationship between the noise that we are predicting using the noise potential network and also this quantum here, having this kind of a relationship between so this is basically the quantity that we are predicting using the neural network, right? And from that, we could also compute the score here, right? So these are all the same thing as like we discussed last time, but you're just like using the sigma and the alpha functions and also the change the time domain. So please keep this in mind. The same thing, basically computing the x1, the output, expected value of the output from the intermediate value based on these two things. So based on this fact, what we are going to do is that now we are going to see the connection between the velocity, basically the vector field, and also this core function. So basically we can see this connection between, we can at least like see that there will be some connection between these two because we have seen this kind of the relationship between the vector field and also the probability path from the Fokker-Planck of the equation, right? So we are basically going to see the same thing without that. So basically the thing is that from our definition of the linear, the Gaussian, the path, the conditional flow map here, now we can compute the conditional the vector field in this way. It's just taking the derivative, right? So we want to also, so this is basically the function of the x1 and also the intermediate data point of the x, right? So also to make this expression as kind of the function of the x and the x1, we are going to replace the x0 based on this fact that the x0 can be computed like this, right? So from our definition of the conditional flow map, now we can basically substitute the x0 with basically this expression. Then now we can see that the velocity, the conditional velocity computed in this way. Is this clear? So this is basically just like some arithmetic kind of things, right? And based on this, what we are going to do is that now the marginal vector field, the UT here. So this is the vector field that we are going to obtain through the neural net training, right? And this can be computed as the expectation of the conditional vector field over this probability path, right? And this becomes basically computing this, but having the expected value of the x1 from the given the intermediate data point. See? Then from the Tweedie's deformular that we have seen in the previous slide, we can simply plug in this Tweedie's formula here. Then what we can see is that now we can see the connection between the velocity and the square function here. So given any kind of the intermediate data point, the x here, for any kind of the time t, the intermediate data point, if you basically have the information of the square function, based on that, you can compute the velocity here, right? Or the other way around, given any kind of the data point x here, if you have the velocity here, then based on that, you can compute the square function. So this means that for the linear Gaussian path, for the conditional the flow map, whether you make it the generative model as kind of the flow the model or basically as the diffusion model, you can basically do some interchange between these two. You can compute one from the other, given any kind of the times that the intermediate data point of the x here. Make sense? So if we go one more step here, so we have seen that there's the relationship between the square function and the noise that we are predicting the diffusion models, right? So based on this relationship, can you also find the relationship between the vector field and also the noise term as well? You can quickly compute this, right? Can you quickly compute this, the relationship between these two? So basically, we're gonna get this, right? So this basically shows the relationship between the noise that we are predicting in the diffusion models and also the velocity that we are predicting in the flow models, right? So from all those like deformulations, basically now you can see. So what we have discussed in this class is that at the very beginning of this class, we started to discuss the generative model, which is defined as kind of the mapping from some kind of the simple distribution, typically the standard Gaussian distribution, to the derivative distribution, right? So this was like all about basically how we are going to define the mapping between the standard Gaussian distribution to the derivative distribution. So at the very beginning, we started with the GAN and the V, and after that, we make that the mapping is kind of the iterative process through the fold process, right? Fold diffusion process, which is basically repeatedly adding some kind of the Gaussian the noise in a way that ends up basically becoming the sample of the standard Gaussian. So this was more about basically define some kind of the conditional the probability path from the all the way from the data the sample to the standard the Gaussian the sample. And in the continuous time domain, we start to see that actually this kind of the iterative process is kind of like equivalent with the stochastic, basically solving the stochastic differential equation. So we could basically find the equivalent, the continuous form, the formulation in the continuous time domain, which is now defined as the stochastic differential equation. And after that, what we have seen is that actually we can find and also the corresponding the ODE, ordinary differential equation, without stochasticity, which is giving the same the marginal distribution. So for all the diffusion model, now we can basically find the corresponding deterministic mapping the process through the ODE, the equation. And now what we are seeing is that actually we didn't need to first define the conditional probability path. We can basically directly define the conditional flow map first. in a way that we are seeing now the diffusion model is kind of some special case of those kind of the flow models. So we can see now this kind of the connection and also all the different perspectives of like seeing the diffusion models and the flow models. I'm not sure whether this will be clear to you. And also one more thing is that for the PFODE, the probability flow ODE, we didn't see how exactly this can be derived from the SDE formulation, right? So without getting into all the details for that, and it's like we are going to see now how this connection between the velocity and also this score function here, this connection between these two is also aligned with the PFODE. So what we can easily see is that, so this is basically the vector field that can be computed from the score function here, right? So this is the equation that we obtained from the previous slide. And given that, if we go back to the PFODE, so this was basically the PFODE formulation that we have seen for the diffusion model case, right? And also the connection between the relationship between the alpha sigma function and the f and the g functions here could be derived in this way. So what we can see is that if we plug in those kind of some of the definitions for the f and the g functions into this equation, we could see that we should see the same equation with this, right? So I recommend you to check this out, whether we can really get the same equation. So if you really put all the things, the f and the g functions into this part, then you're gonna see that actually we are getting the same equation. The same equation showing the relationship between the vector field and the score function. So the derivation of the vector field, the velocity obtained from the conditional vector field and also from the probability, the flow, the ODE are basically identical. So basically from this, we can see some kind of all the connections between the diffusion models and the flow models and how these are also related, how the conditional probability path is also related to the conditional flow map and also the vector field as well. Okay, great. So this is kind of key thing. So basically the diffusion models and the flow models are mathematically related in a way that if we define the conditional flow map as kind of linear Gaussian path like this, in the form that we have seen in the Bayesian diffusion models, then these two basically become equivalent in the mathematical form. The only difference is that whether we're going to basically train a neural network for the noise or train the network for the velocity. But obviously, once you train, basically learn one of these two things, based on the noise, you can also compute the velocity, and on the velocity, you can also compute the noise. So I strongly recommend you to try this kind of conversion for the models that you already implemented in the first assignment. So what you need to do in the third assignment is that the first assignment was to implement the DDPM and the DDIM, right? And also I told you that you could basically, and also the second assignment was basically running the generation the process by solving the ODE, right? Using the DPM solver, the idea. Now you can basically also perform the generation the process by switching the noise into the velocity and perform the ODE. So it will be basically equivalent, it's the same as you have done in the second assignment. What you will need to do in the third assignment is that now even you are not learning the noise, but strictly learning the velocity. And then based on that, you just perform the ODE in the generation the process. So we are seeing some kind of all the variations of like in terms of like how, the way that we can basically train either diffusion and the flow models and also perform the generation the process of the diffusion and the flow models. Makes sense? But this is the thing. The flow, basically these two become the identical when you basically define the conditional the flow map as kind of the linear the Gaussian the path. But the flow map is kind of the more, you can think it's kind of like more the general concept in terms of that it can basically generalize the diffusion models in multiple ways. The first thing is that the conditional flow map does not need to be the linear form. So you can also explore many different options you can design your own the conditional the flow map in many different ways and see whether this can really improve the performance. Also, we have some kind of the graduate students, like just playing with some kind of the non-linear kind of things, like some quadratic, whatever sort of things, and see whether this can really improve. I guess the answer was no, but yeah, you can try many different options for the conditional the flow maps. And more importantly, for the flow the matching, the thing is that if we go into the more the arbitrary the conditional flow maps, then now we can consider the case, making the reference distribution as not as kind of the standard Gaussian, but any arbitrary distribution. So the good thing of the flow the matching is that now we can consider basically mapping two different distribution. Even we can consider learning some kind of the mapping from like the one data distribution to the another the data distribution. This is even possible in the concept of the flow models. So you can think that the flow model, and also the flow model is the case that we are now using the ODE, while the diffusion model has been introduced from based on some stochastic deformulation. So you can see some kind of the differences and on how the flow models basically generalize the idea of the diffusion models. Any questions on this? So I don't know how you would feel it, but actually this is kind of the most interesting part in this class. I mean, how all those things are basically connected to each other and how the same thing can be basically explained in all the multiple ways. So I recommend you to check out some more details for those kind of connections. And actually, one more reason like why we discuss the flow model is that basically we're gonna see that many recent models are now using the flow matching, not the diffusion models. And one of the reasons for that is that it becomes much easier in terms of like accelerating the generation of the process through the fine tuning. So last time we have seen the idea for the consistency model, which was also kind of some simple idea in terms of like accelerating the generation of the process through the fine tuning. So here basically we're gonna discuss the same thing, basically how we can accelerate the generation of the process with some kind of the fine tuning. So for that, so the thing is that this is like very new topic, so still people are using some kind of the mixed the terminology for the same thing. So to simplify all the things, from now we're gonna say the conditional the flow matching the model as like simply just like flow model. And we also have seen the two options for the trajectory, right? The linear, the conditional the trajectory, and also the diffusion the trajectory. So for the linear, the conditional the trajectory, people typically also call this the term the rectified the flow model. Okay, so let's assume that we are basically targeting this kind of a rectified flow model. And for the any flow model, the training procedure becomes like this. So this is the same slide that for the general case, what we can do is that we sample the x1, the data point, and the sample from the standard Gaussian. It does not need to be standard Gaussian distribution. It can be any reference distribution. So based on these two, what we can do is that we are computing the intermediate data point xt using the predefined the conditional flow map, and also computing the velocity by just taking the derivative and basically computing the L2 loss to train the velocity neural network. So what we can see is that in the training of the flow model, this sampling process is basically involved. We are taking any random pair of the x0 and the x1, the data point, and also the standard Gaussian sample. The thing is that even when we basically train a rectified model, which is basically having the conditional, the linear trajectory, the output trajectory may not be linear. So let me first show this slide here. So what you can see is that, so these are all the kind of a conditional trajectory for any arbitrary sample from here to here and here to here. So this is the case that we are taking this as kind of the two Gaussians as kind of source distribution, and also the two red, the dots here, the groups of the red dots as kind of the target distribution. So if we see the conditional velocity at this point, depending on which pair you choose, the conditional velocity can be either this or this, right? Can go up and can go down, right? So which means that if we compute the expected, the value here, basically if we compute the marginal velocity at this point, the marginal velocity may not be either this way or this way. It can be like go this way, for example. So which means that even when you basically make the conditional trajectory to be linear, the straight line between these 2 points, if we compute the marginal velocity at the end through the trained neural network, then the flow map, which could be computed based on the marginal velocity, may not be straight. It may result in this kind of some banded curves like this. Makes sense? So the linear trajectory is only for the case like when you have to basically take these samples here and also the another sample here. For any 2 points, obviously the conditional trajectory between these 2 dots would be straight. So that's how we defined. We defined the conditional trajectory as kind of a straight line. But as you can see, like depending on which the 2 points, 2 endpoints we choose, even the conditional velocity at this point can go up or it can go down, right? Which means that at the end, the marginal velocity can be something like this at this point. And the flow map, the marginal flow map that are basically defined based on the marginal vector field may result in this kind of the curved trajectory. Then what would be the issues with the curved trajectory? Can you see? Yeah, so because like we are now computing all this kind of the trajectory by solving the ODE, right? The trajectory is basically defined based on the velocity. So if we had this kind of some straight trajectory like this, the good thing is that from the starting point, if we know that this kind of the case, but if there is such kind of case that the margin of the flow map is kind of a straight line, which means that from the starting point, if you predict the velocity, then you can go straight all the way to the end point here. Which means that now you can make the one-step degenerative model. You don't need to have any kind of iteration. The reason like why we still need to basically compute the velocity multiple times is that we are having this kind of the banded trajectory. We cannot go straight all the way to the end because we know that the trajectory will be banded like this. So that's why basically we need to basically chop the kind of the time domain in a way that basically going one small step and just like going another small step and just repeat those kind of things. In terms of solving the ODE, right? So what we can see is that it's always good to find some kind of the straight trajectory mapping between the points in the source distribution and also the points in the target distribution. The problem is that even when you basically define the conditional the flow map as kind of the straight trajectory, the output, the marginal trajectory may not be straight. So that's kind of the issue. So some kind of the simple way to make it straighter is that, while skipping some details here, is that, so previously to train a diffusion model, what we need to do was that basically taking the random pairs from the source distribution and also the target distribution. The simple way to make it straighter is that once you basically have any kind of the pre-trained the flow model, we are using the pre-trained the flow model to take the pair, the sample of those kind of the pairs of the x0 and the x1. So let's say we now fine-tune the flow model by just not taking the random pairs of like x0 and the x1, but by performing the generation of the process using the pre-trained model and just taking these pairs. Then surprisingly, then what we can see is that when these are basically the trajectories that we could see from the first rectified model, the rectified flow model, after another fine-tuning, which is called the two rectified model, for the two rectified model, you can see that now the trajectory become like this straight like this. If you repeat this one more time, then you're gonna get even straighter the trajectories like this. So these are some kind of the very simple the tricks, and obviously there are some kind of the loss of the theory in terms of like, why we are achieving straighter the trajectories with the fine tuning. But after skipping some kind of details here, for the flow models, the way that we can basically make some kind of the faster degenerate model is that you first train a flow model, and based on that, fine-tune the models by just taking the pairs from the previous model. Then you're gonna get the straighter and trajectories, which means that even with the fewer number of the time steps, the ODE solver, you're gonna be able to get some kind of clean the outputs. So after some kind of a couple of the iterations of like fine-tuning the model, now what we can do is that now we can make some kind of even a single step model, which means that from the sample of the standard Gaussian, we can directly map this point into the one of the data point. So this is kind of interesting, right? We actually started from the one-step model. VAE again, those are basically the one-step model, right? We have seen that actually there are lots of kind of the disadvantages in terms of the diversity or the quality of the outputs. So that's why we started to basically discuss the diffusion model while basically sacrificing the computation, the efficiency with the iterative process. And now we are going back to the one-step model, basically through this kind of the fine-tuning techniques. In terms of that, now we can get the fast speed and also the good quality as well. So actually, if you see the many recent the image and the video generated models like state diffusion D3 and the flux, those things, you'll be able to see that those are basically not based on the diffusion the models, but based on the flow models. Basically, these are basically identical, but you can see that at least they are not basically predicting the noise, but predicting the velocity. And if you remember what we have done in the first lecture, do you remember this slide? So at the very beginning of like this class, I was asking you to try to make some generate some kind of images using the flux model. So actually, this flux conditional, this one, this is the model which is basically trained based on this kind of the reflow technique. So you can go back to this model and see how this model has been was trained. And also one more thing is that we also discussed the concept model for the diffusion, and also now discussing the reflow technique for the flow models, right? So these are kind of some rival in terms of the just like competing each other, and see like now we are still seeing some kind of the competition between these two in terms of like which one is basically better for the view step degeneration. So if you see some kind of some comparison here, the CD and the CT, those things are like all based on the consensus models, and the FID goes down to 4 or 3 here. And also with the 2 rectified flow, we are also seeing some kind of a similar FID here. Yeah, for the 1 and the 2 steps. So you can see that these are some kind of the 2 very different approaches in terms of how we can accelerate the generation the process using either the diffusion models or the flow models. Any questions on this? Okay. So this is the end of the kind of discussion for all the basics for the diffusion models and the flow models. So we discussed basically how the idea has been evolved from the VAE GAN to the DDP and DDIM, and also the SDE and the ODE formulation, and also the flow models. For the rest of the 3 weeks, we are going to see more into the application side. So basically, not only in terms of generating some kind of like some realistic data points, what can you do more in terms of getting something not just like realistic, but something that we want to see. How we can basically inject some kind of the user preference in the generation process. So for the next week, we are going to discuss the inference time guidance, which is basically injecting some kind of the user preference at the inference time without any kind of training. And also we're gonna move on to the diffusion model, the case for the discrete data in the week after the next week. So this is the schedule. Okay, let's end the lecture here.
For the test.